Right, I think I'll get started. I wasn't clear if there was supposed to be someone to come and introduce me, but no one's here, so I'm going to assume I introduce myself. So, hi, I'm Christopher Jefferson. I'm a reader at the University of St. Andrews, for those who don't know me. So a bit of background. So I've done a bunch of stuff writing constraint solvers. I wrote the Minion constraint solver, which does still exist. We're just very bad at making releases. You can go and find it on GitHub. I also do a lot of research in group theory. So I've done a lot of work in writing group theory algorithms. This work isn't in constraints specifically. It's presented at maths conferences. But a lot of the ideas that I use in that are the same ideas that are things I've taken from constraints. Unfortunately, if that sounds very interesting, this is not about that. This is about applying symmetry to constraint programming. I'm going to start with a picture of a snowflake. I don't think you can have anything about symmetry without a picture of a snowflake. I think it's mandatory. So this is going to be a fairly, I'm going to start at a very low level because I think a lot of people have a poor understanding of the basics. This does mean there's going to be limited opportunities for me to get into all the work that everyone's done. You could not possibly discuss every paper people have done in symmetry. There is huge numbers of them, hundreds and hundreds of papers. As a bit of an experiment, it may or may not work. In the chat, I've put a link to a Google document. If there are any symmetry papers where you think people should read this paper and no one ever reads it, then go and put it in that document. Like, anyone can edit it. If you can't edit it, let me know in the chat. And if you have any comments while I'm speaking, or if at any point the audio or video cuts out, put them in the chat on Hoover. But feel free to edit it, put in anything you like. There will be some audience participation in this talk. I'm going to ask a couple of questions. I'll let you know when I get to them how to answer them. So, bit of an overview. I'm going to start by talking about what symmetry is, which is a question I think is trickier than many people expect. There's been a bunch of papers, I'm not going to evilly name names, where people have got the definition of symmetry wrong, in my opinion. Then how we find it, how we break it in theory, how we break it in practice, and how we also, if you really have to, how you can break all symmetry, which sometimes you really have to break all symmetry. This is particularly common for me when I'm working with mathematicians. Sometimes they'll say, no, I need to know all of the symmetric objects. Oh, no, I've been told that the document isn't editable by other people. I'm going to very quickly check if there is a button. If there is a button I can click on to make it editable. Anyone with the link can edit. Doing things on the fly. Let's see if that one works better. If not, I won't play around, but we can do it at the end. So I'm going to start with a nice, easy symmetry example. So this is the symmetries of the square. The problem I'm showing here is the n queens problem. So you have to put n queens, in this case represented by little blue circles, on a chessboard such that no two queens can attack each other. And the chessboard has a bunch of classic symmetries. You can pick a chessboard up and you can rotate it by 90 degrees, 180 degrees, 270 degrees. Bit harder to do with a real chessboard. You can reflect it in a symmetry axis down the middle. Imagine you turn it upside down, but the queens didn't fall off. So there's these 8 symmetries. And the idea is, most of the time, we don't want 8 solutions. We want one of them. They're all in some sense the same solution. So here's a nice quick bit of audience participation. So the 3 queens problem. So you've got to put 3 queens on a chessboard. How many symmetries do you think this problem has? And the questions I'm going to ask, there is not usually a right answer. There's not like a single good answer. If you go to this website that's listed at the bottom, menti.com, and you should hopefully find, you can enter code, and I'm just going to try it to make sure it works, 710221. And then you should be able to find, you can enter a number and see what people think. So go on, like have a think about how many symmetries would you say this problem has? I have a few answers now. Oh, I've got another one. I have a few answers, so I'm going to bring them over so you can see the answers. Oh, so hopefully this is showing up. So we've got some 8s, a 1, a 9, a 4, a 10. What the answer is, I should have given you like a text box so you could type it. I should have asked you to like say why you think that was the answer. What you think the answer is does depend on how you define the symmetry group. So if you're not aware of this, what's interesting about the 3 queens is it doesn't actually have any answers. There's no way of putting 3 queens on a chessboard such that they can't attack each other. If we define a symmetry as something that takes solutions and turns them into solutions, then, well, in some sense, anything's a symmetry because there's no solutions to map. And in fact, I wrote a paper on, so we could say symmetries have to map solutions to solutions. That feels like the right kind of thing to do. What if the problem doesn't have any solutions though? Then it's kind of everything's a symmetry and that feels wrong. We could also require symmetries map. It feels sensible that they map assignments to your problem to assignments to your problem. But, oh, sorry. But if we look at this bottom picture here, this is the n queens problem I showed earlier. So assume, and this is a common way people do this in CP, every row is a variable. So you have a variable for every row to say where the queen goes on that row. So the left-hand side, it's not a solution to the n queens because there's 2 queens in the first column, but it's certainly a reasonable way of assigning the variables. If we flip along the diagonal, now the first variable takes 2 values and the 4th variable for the 4th row takes no values. And now that's not how constraint problems work. So it's not obvious what you should map. If you decide to say that you're allowed to rearrange the grid in any way you like, and all you care about is mapping solutions to solutions, then these are the number of solutions to the n queens. So ignore the binary no goods column. So this is from a paper I wrote many years ago about defining symmetries. So you can see like the 3 queens, you can just rearrange the 9 cells however you like. And then 4 and 5 have big ones. 6 has this ridiculous symmetry group because it turns out there's quite a lot of squares on a 6 chessboard that you can't put a queen on in an n-queen solution. And then once you get to 7, you just get the 8 symmetries you would expect. So there's a kind of there's enough solutions that you don't end up with weird extra symmetries. And you get like 7, 8, 9, 10 as you would expect. 7, 8, 9, 10. And onwards, you always get 8 symmetries. So yeah, so how do we define this? Usually what we say is that symmetries have to map solutions to solutions. And then we just accept that we might not know all the symmetries of the problem in advance. We will hopefully know some of the symmetries, ones that we can find, but we won't know all of them, because finding all the symmetries means you know all the solutions. And if you know all the solutions, like usually you don't care anymore. You do sometimes. So yeah, so there's 2 ingredients to a symmetry definition. You have to decide what is the thing you're acting on, what's the symmetry allowed to do, and also what is the condition that must be preserved. And usually it's solutions. So a little bit of group theory background. So group theory is a massive research area. There's like many conferences. It goes back hundreds of and thousands of years. And there are so many papers on the topic, and we're not going to discuss that stuff in depth. For our purposes, we're interested in permutation groups. So permutation groups are a type of group. So you have a bunch of things, which I'm going to call X, and then you have a bunch of bijective functions that rearrange X in some way. So in the case of the n queens, they rearrange the positions on the chessboard. If you have a symmetry that just rearranges the variables of your problem, they might rearrange the names of the variables. You can also have value symmetries that rearrange the values of your variables without moving the variables. The important thing about a group is that you have the identity function. For every permutation, you have the inverse of the permutation, so you can always go forward and backwards. And if A and B are permutations, then A sort of applied to B is also a symmetry. In constraint problems, these are kind of all obvious, as in if you like in any problem, if something's a solution, you don't do anything, it's still a solution. If you have a way of transforming it, you can usually go back. You can have things where you go and don't go back. These are called dominances. I'm not going to discuss those greatly here. What's good about group theory, and we kind of this is used a lot underlying, a lot of algorithms on groups are very efficient. A lot of algorithms, their complexity is in the number of things that you are permuting, not the size of the group. So on like 10 objects, there is 10 factorial ways of rearranging them, but the complexity of algorithms on groups is usually like order 10, not order 10 factorial. These algorithms are quite complicated. They're not trivial by any means, but a lot of them are polynomial time. And often under the surface, if you're using computational group theory systems, you're using this fact. What do we want to act on? So some papers, and I'm not going to be mean and name names, will say that a symmetry is just anything that takes the set of assignments to all variables and permutes that set around in itself. The problem is that's too big. If you're allowed any way of mapping the assignments around, then a bijective function on the set of assignments basically just has to be a function that maps every assignment to another assignment. The function is massive. It's as big as storing all solutions to the problem, well, bigger. So that's terrible. You need the set of things on which your symmetry acts has to be small enough that it's not expensive to store and manipulate. So the three classic ones are you just permute the variables, you just permute the values, or you permute the literals. So literals is a word for like a variable value pair. So it's like x equals 2, x equals 3. Those are literals. And literals seems to have become the standard thing to apply symmetries to. There's as many of them as there is variables times values, so there's usually not a ridiculous number of them. If you're doing like integer programming or linear programming, you might want to just act on variables, because if you're doing linear programming, you have a very large number of values, infinite number of values. And integer linear programming can still have huge numbers of values. So you might just do variables. So literal seems to be the sort of place everyone has settled in constraints. This does mean that when we apply the mapping of the literals, we have to map solutions to solutions, but we might map things which are not solutions to just some mess. We might map like some variable might end up with 2 values and some other variable end up with no values, and that's fine. We're just happy with that. Yeah, so generally we map solutions to solutions. If you're doing optimization problems, you normally map assignments to other assignments of equal value. But how do we find the symmetries? It is as hard to find the symmetries as it is to find all the solutions. So we cannot, in general, theoretically find all the symmetries. And usually it's no good to find them after you've finished, as I said. So as a nice and easy problem, we could say, here's a constraint problem. So I've got like a plus b is greater than 4, c plus d is greater than 4, a times b times c times d is less than 100. And we could say, like, what are the symmetries of this that permute the variables? Now, we could go away and we could solve the problem and come back and try to look at the solutions. But also, just looking at this, you can be like, well, clearly you can swap A and B, and clearly you can swap C and D, and clearly I can swap the pair AB with the pair C and D. And we encapsulate this usually by building a graph. So here I've built a lovely graph. So there's a lot of stuff going on here. So we have a set of nodes which represent the variables A, B, C, D, and then we represent all of the constraints. So we are going upwards, we're like A plus B, we add them, and that is greater than a 4, and then below we multiply them all and say that is less than a 50. When you build this graph, there's a few things you have to be careful with. So notice that from A, B, C, and D going down to the multiply, all the arrows point to the multiply, because we want you to be able to switch like the A, B, C and around freely in the multiply, because A times B is the same as B times A. With a less than, we mustn't swap the left and right hand side and the right hand side of a less than. It doesn't make sense. So if we had an equality, we would want to make a graph where you could swap the two things at both sides of the equality. If we have a greater than or a less than, we have to say no. You have one arrow. So usually people do this by making a directed graph and just making sure that one arrow goes in and one arrow goes out. Also, the colors are important here. What we define as a symmetry of this graph requires that we map things of the same color to other things of the same color. So the variables can all switch around freely, but like fours have to map to fours, less thans have to map to less thans, greater thans have to map to greater thans. And usually if you sort of try to do this, you get a very, if you just kind of hack this, you get a very reasonable thing. Like I say, you need to deal with, you don't want to turn A times B times C times D into kind of A times B, which you then multiply by C, which you then multiply by D, because that graph doesn't have as many symmetries. And then we find the symmetries of this graph, and then we found the symmetries of our problem. Well, we found the constraint symmetries. These aren't all the symmetries, but they seem like an easy set to get. As I say, it's easy to lose symmetries or let fake ones sneak in. Look out for commutative associative operators. Make sure equal values and swap. You can make this graph where instead of variables, you have literals. So then you'll have all the literals. It becomes harder to encode the constraints. Constraints like some are relatively difficult to encode on a graph. On the other hand, if you have a sum constraint, it is extremely unlikely that you would be able to permute the values. I mean, your problem, like some constraints intrinsically care about the order of the things that they're adding. You might be able to permute the order of the variables, but not the order of the values. Just to say something else. So then, of course, now we have this graph. What do we do with it? There are tools which will find the automorphism groups of graphs. So there's programs like Naughty and Saucy and Ferret, which is one I work on. And there's lots of systems. In theory, these systems are all exponential case worse time complexity. None of these systems run in less than exponential time in the worst case. You can construct constraint problems where these systems will take longer to find the symmetries than it would take you to just solve the problem. But you are almost certainly never going to construct such problems. I have never seen a real constraint problem where the problem took any amount of time to solve. Other than if your problem is something to do with graphs and your constraint graph includes a big awful graph, and it is one of those graphs which Naughty finds very difficult, but then you've kind of cheated. You've kind of hidden a problem Naughty finds difficult in your problem. So in theory, detecting symmetries is expensive. In practice, it's incredibly cheap. But we don't want to have to go and detect symmetries if we don't have to. So in particular, nowadays with languages like Minizinc and Essence Prime and Essence, if you're going to build your graph, you have to build the graph for every instance. You have to take your Minizinc, substitute in your parameters, generate the output, usually flat zinc or something where you've at least done put all the parameters in, and then calculate graph automorphisms on that. An obvious question is there some concept of graph isomorphism on a like parameterized family of graphs? And the short answer is no. You can't say, I have this class of graphs, tell me what the class of symmetries they have is. It basically doesn't work. You can sometimes do it for very trivial problems. But when you have like a Minizinc model, it would be nice if you could just find the symmetries once and not have to keep finding them over and over again. You can do this by hand. You can take your problem, you can put a few instances in, find the symmetries, and often at that point it becomes easy to understand the symmetries, and then you can just encode them, convince yourself you've got them right. But it is nice if you can automate this away entirely. So there is work by Chris Mears et al., where the idea is you take your Minizinc problem, you apply some transformation to it. So maybe there's like some matrix and you swap the indices, or you swap two values in the domain of the index of two values in one of the indices of one of the matrices, or swap two variables. Then you try very hard to take this new problem and prove it's the same as the problem you started with, which means you found a symmetry. And you can do this in simple methods. You can do this by just taking the problem and trying to renormalize all of the expressions and see if you end up with the same thing. You can also go as far as using theorem provers to prove they're the same thing. These techniques are very expensive. On the other hand, you only have to do them once for the class. And once you've done it, it's great. They are surprisingly effective. They do find a very large number of symmetries. I would not attempt to implement one of these yourself unless it's your research area. It's very difficult to do. But they are very clever. The other thing you can do, and so a brief bit of personal bias, I work on a language called Essence. I'm now going to tell you Essence is great. I obviously might be biased against the language that I work on with people at St. Andrews. Many symmetries in practice appear to come from having to make things concrete, which were originally, like in the original problem specification, it was all more sort of vague. And then it became concrete. So I'm going to explain what I mean by this. So this is Kirkman Schoolgirl's problem, which I have chosen not to edit from the original problem. So I apologize for any sexism, but this is his original problem. So there's 15 young ladies in a school, walk out 3 abreast for 7 days in succession. So each day they're 3 abreast and there's 5 rows. It is required to arrange them so no 2 shall walk abreast twice. So at a high level, this is saying, right, each day we need to organize the girls into 5 groups of 3, and then we need 7 days. The problem is when you go and put that into your constraint solver, first we have to label the young ladies. So I don't know, probably 1 to 15. So now we've labeled them. We've introduced a symmetry when we labeled them. We also, each day, when we have 3, you probably in constraints will have like 3 variables, like the first, second, third. So we'll have to label those. Then we're going to have to, probably you put that in a 3 by 5 matrix. So now you've ordered the rows of girls. And finally, you have to put that matrix 7 times for the 7 days of the week. So now we've ordered the week as well. So in the process of constructing a constraint model, we typically constraint solvers love lists. And so we've had to make all these lists everywhere. And whenever we made a list, we had to order something and we introduced a symmetry that wasn't there in the original problem. Arguably, you can argue whether they were in the original problem or not. So the idea is, in essence, what we would write is we would just say, make a new type G of size 15. So this new type, we don't name the things in the type. We're just saying we want to type of 15 things. Then we say, find a set of size 7, that's the 7 days, of partitions, and these partitions, each cell of the partition is of size 3 of G. And then we'd write the constraint saying that 2 don't walk abreast. And now this doesn't have any symmetry in it. Now the system, when it turns, now this isn't magic, like this has to be turned into a constraint model. But when it's been turned into a constraint model, at every point where you introduce symmetry, you immediately deal with the symmetry. And because you introduced it, it's easy to make sure you deal with it when you introduce it. This isn't perfect. I'm going to discuss later on that the combination of value and variable symmetries can be difficult to deal with. And indeed, it is still difficult to deal with here. So the fact that we have the symmetric girls and the symmetric days, dealing with this isn't trivial, but at least you clearly understand what your symmetries are. So why do we want to deal with symmetries? So one reason is you want to avoid producing symmetric solutions. So you don't want your list of solutions to have like 100 things that in some sense fundamentally are the same thing. In practice, what is almost always more important is avoiding symmetric search. You don't want to keep generating, you don't want your search to say, oh, let me try assigning, I don't know, x is 1, it goes off, it does a whole bunch of work, proves there's no solution where x is 1. If the values are symmetric, you don't want it then to try x is 2, like no, x is 1, it didn't work, by symmetry there's no point trying the other values of x. This is also, just to briefly mention, people who work on local search have a bit of a love-hate relationship with symmetry, because in local search, sometimes adding symmetry breaking constraints helps. It frequently hurts because they're, like the symmetric solutions are good. If you're local searching, you're searching around. There being more solutions is good. There's more things for you to stumble across. So don't blindly apply symmetry breaking in every area. Broadly speaking, there are two families of symmetry breaking. There are static techniques, which is where you add a constraint, add a bunch of constraints and then solve the problem using your solver as normal. And then there's dynamic symmetry breaking, where you adapt the search to avoid searching symmetric things. These both have positive and negative points, which I'm going to discuss. If there's anyone in the talk who wants to disagree with the following statement, please do so. You can even turn your microphone on and argue with me. Broadly speaking, static symmetry breaking has won. There are advantages to dynamic symmetry breaking. In some places, it's very important, but most of the time it is much harder to implement. For a start, it requires changes to the solver, and the benefits are not worth it over dynamic symmetry breaking. Now, those of you who were not around in the field in 2000, which makes me feel old, because I was, there was like really significant static versus dynamic wars in the early 2000s. Like people would go to each other's talks and ask purposefully mean questions to like, oh, I think you'll find your dynamic symmetry breaking method has the following flaws. And like everyone's happy now, but it got quite vicious for a minute. It was acceptable to cross. So my thesis had static symmetry breaking in it. There's someone called Karen Petrie. Her thesis was all about dynamic symmetry breaking. We got, so like, even though we were both on the opposite sides of this battle, we got married. This is completely irrelevant to the talk. This is our wedding cake. So just a brief like break in the middle. Not in the middle, brief break. At our wedding, it was, I felt I wasn't getting enough to do, so I was told I could organize the wedding cake, because I was told, how can you mess up a wedding cake? I didn't mess up a wedding cake. I made the best wedding cake. My wife loved it too. My mother-in-law less certain about it. Anyway, so even though we were on the two sides of the war, we got together. So nowadays everyone's friendly again. But there are these two techniques, and I'm going to talk more about static than dynamic, mainly because static is a thing you can easily implement yourself. If you want to implement dynamic symmetry breaking, you're going to have to go and read the papers, and they're long and complicated and very clever, but there's a bunch of work to do. So to give like a basic idea of how static symmetry breaking works. So assume we have our symmetry group now, and it is acting on some object X, so the assignment. So we have our group, and it's taking the solutions and it's mapping them around. At this point, we assume we don't know what the solutions are. So we assume it's mapping, it's taking something, so bags of literals, solutions, whatever, assignments, sorry, and like mapping, the group maps them around. And the orbit of if you take some assignment and you take all the places you can get it using the symmetry, we call that its orbit. So given one thing, you have the orbit, that's all the other things you can get to, which are the same solution. So once again, going back to the n queens, each of these, all of these things are in the same orbit, and this is the full orbit. So if you have one of these, you keep applying elements of the symmetry group, and you get around to all the other ones. And typically, what we want is one of these. We don't want more than one. So sound symmetry breaking, we have to keep at least one of them. So for example, if I just wanted a really quick symmetry breaking technique, I could say the queen on the first row has to be in the first half of the row. And that would knock out the following four. You can hopefully convince yourself this is sound. In any chessboard, there must be a queen on the first row, in any solution, certainly. If we, and if it's in the second half of the row, we can reflect it so it's in the first half. You also want your symmetry breaking, like it's really important it's complete. I've never totally liked the definition of complete, but this is the standard definition. Complete means it keeps at most one solution. So a symmetry breaking method can be complete because it deletes all the solutions. It's not valid anymore, but it's still complete. So let's have a go at making some symmetry breaking methods. We could go through every orbit in turn, pick one of the things in the orbit, and add constraints to delete the other things. This is a terrible idea because we'd end up with certainly one constraint per solution, and also one constraint per each, like a possible assignment. So what we do, instead of considering each of the orbits in turn, we add one set of constraints that blast like everything out of, in each orbit, keep at least one thing. Hit them all at the same time. I'm going to explain the type of thing that we do. So here's just a quick example. So imagine the matrix on the left. Imagine the symmetry is that you can swap the two rows. So you can swap the first row with the second row. We could say that the first row has to be less than or equal to the second row. And this is sound. If you have a matrix, one of the rows is smaller, or they're equal. And it's complete. If you have a matrix, either both rows are the same, in which case if you swap the rows, you get the same thing. Or one of the rows is smaller, in which case that row gets put at the top. Similarly, I could break column symmetry. So here I say, right, I'm going to say like the last column is smaller than the second to last column, and the second to last, the middle column, and the middle column is smaller than the first column. And in the same way, the columns end up nice and ordered from smallest on the right and largest on the left. So you might then, and then the obvious thing to do is you go like, right, now we chuck all the symmetry together. We like chuck all the symmetry together and we say like, right, you put the two symmetry breaking constraints on, and then if you add row and column symmetry breaking, this would break all the symmetries. So this is our next question, and I'll pop this up here to remind you what the magic code is. What is going on? So if you've forgotten the Menti code from earlier and you've closed the page, this is hopefully written at the top. So is this symmetry breaking method sound, complete, sound and complete, or neither sound nor complete? Now, because I've put the page up, you can see what it is. You can see what other people are guessing. But like, remember, this is anonymous. Hopefully you didn't have to log in. So if you have logged in, I'm not going to save it. So don't worry. No one will know what you chose.
Shows no one's read my paper.
Now, so okay, if someone's written a paper on the topic, I hope I've got the answer right. I did double check this morning. So the answer, and I was being a bit sneaky with this one, is it is complete. It is complete, but it is not sound. If you are familiar with row and column symmetry breaking and you just thought, oh, I know how row and column symmetry breaking works, I have ordered the columns from largest to smallest. Not if the columns are ordered smallest to largest, which is what people normally do, then it would be sound but not complete. But there are matrices where there's no way of ordering the rows smallest to largest, but the columns largest to smallest. However, given any matrix, if there is any way of doing it, there is only one. So it is still complete. As I said before, complete without soundness is just stupid most of the time because like it saves something. So the point here is it's irritating. So you can kind of try, usually breaking like bits of your symmetry group is easy, but then when you try chucking everything together in a bag, it breaks. So fundamentally, and if you take one thing away from this tutorial, it should be this bit. There is a thing called the Lex-Leader, and it's great. And it's basically the basis of almost all static symmetry breaking. And the bits of static symmetry breaking which were not derived from this, in retrospect, almost all, not quite all, almost all can be derived from this in retrospect. The idea is it requires Lex constraints, which are implemented by every solver efficiently. Mainly, they're implemented efficiently by every solver because everyone wants to do Lex-Leader constraints. You can encode them efficiently in SAT. I'm going to give some examples. I find this is one of those things where it's tricky to write the maths down and it's easy to understand. So we go back to our chess examples again. The idea is we imagine that we read off these matrices, left to right, top to bottom. Imagine they were one very long line. And we'll treat an empty square as a 0 and a queen as a 1. So the first board goes 1, 0, 0, 0, 0, 0, 0, 0, the end of the row, and then we keep going the next row 0, 0, 0, 0, 0, and then 1, 0, keep going through. And we say we want to pick the lexigraphically smallest solution. So whichever the solution is we pick, if we apply a symmetry to it, it should get bigger or stay the same size. So in this case, this one, I hope I got it right, is the lexigraphically smallest solution. So because I said that queens were 1, it is definitely this one or this one, because they're the ones where the queen is at the end of the first row. And then in this one, the queen's in the 3rd place, and this one it's the 2nd place. So I did indeed get the right. And so we say, whatever the solution is, if I apply a symmetry to it, it must not get smaller. And if we put that on for every symmetry, we'll end up with the smallest thing in the orbit, because every symmetry we apply makes you bigger or equal. There can be symmetries where you apply the symmetry and you get the same thing. That's fine. You don't want to delete those unless you're doing some clever streamlining or something clever. So for example, you can write down so now I'm doing row and column symmetries again, and you can write down all the constraints for a 2x3 matrix. There's 12 of them. And if you put all those on, you break all the symmetries on a 2x3 matrix. I'm just going to highlight a few of these just to sort of show some things. So are we done? So we find the symmetries, we apply Lex-Leader, symmetry done. If your symmetry group isn't very big, and by isn't very big, I would typically mean smaller than about 10,000. Yeah, basically just chuck all the constraints in. Most solvers can cope with 10,000 Lex constraints. It's fine. But the groups can sometimes be too big, so we need to do other things. Even for simple problems, the number of symmetries can get huge. So back to the schoolgirl problem again, I figured out the number of symmetries. So we have the 15 schoolgirls, the 3, the 5, the 7. And so we end up with, I'm not going to attempt to pronounce what that number is. That is more constraints than constraint solvers will accept. So we have to do something else. There are 3 techniques we can use to attack this. We can try to find a smaller set of constraints that still do all the symmetry breaking. And this happens relatively frequently, particularly if your symmetry group is quite simple. We can write special algorithms that do the same symmetry breaking, but faster. These are less common. So often there's some cases where they're faster, but they're still exponential time in the worst case. Or while we have this massive bag of constraints, we can just use some of the constraints instead of all of the constraints. That'll get us some symmetry breaking, which is better than nothing. So to pick the very simplest example, the very first thing, most people don't even realize they're doing symmetry breaking. If you have a list and you don't care about the order of the things, just order the things in the list. Say the first one smaller, then the second one, then the third one, then the fourth one. This is exactly what the Lex ordering would tell you to do, but on n variables, the Lex ordering would generate n factorial constraints that did this. And you can obviously just order them with less than or equal constraints. There is a good reason to know what you're doing came from the Lex order, which I'll discuss later, which is when you're trying to combine symmetries. If they all come from the same Lex-Leader, you can throw them all in the bag together. You know they're all compatible with each other. Also, symmetries are often, so there's different ways of symmetries nesting inside each other. So the idea, so if you ever want to look this up in a group theory textbook, it is called the imprimative action of the Reef product. I am not going to define any of those words, but if you are a mathematician, you'll know what that is. And if you want to go read a maths book, you can go look up that phrase. I'm going to temporarily assume that the girls have become named. So they're not symmetric anymore, but the other parts are still symmetric. So the girls' breast can still swap, and the order of the rows in each day can swap, and the days can swap around. You can order in each row on each day, you can order the 3 girls in the row. And the idea is you can order, if you order every row of 3 girls over all of the days, you've broken that bit of the symmetry. but the rest of the symmetries are still there, but you've completely broken the symmetry of the girls in each row. Similarly, you can order the rows in each day from smallest to largest. And then finally, you can order the days by considering it as a matrix. For this to work, you need that the symmetries in each day are independent. So the idea is in the first day, I can shuffle the rows, and in the second day, I can shuffle the rows, and I can do those things completely independently, which means that I'm allowed to break them independently. Similarly, in each day, I can rearrange the people in each row completely independently of all the other rows. So I can break each of those symmetries independently, and everything is fine. This does not apply to the symmetry of the girls, because if I permute the girls on one day, I permute the girls on all of the other days. The symmetry is there. This is not the refaction. This is something else. So you cannot use that. So we can use this to break almost all the symmetry, but not the symmetry of the girls. And irritatingly, you can't just now kind of do the symmetries of the girls separately. Like you've started symmetry breaking. So yeah, basically there isn't a way of doing all symmetry breaking in this problem easily and break all the symmetries of the girls and the rows and the days and everything. If you like, the way you would prove this, if you wanted to do, just to give you a feeling, I'm not going to do a proof in depth, but all symmetry proofs tend to take this general form. First, you prove it's sound. You prove for any solution, you've still kept a solution. So in this case, we could prove, well, if we order in each row, and then we order the rows by smallest to largest, and then we order the days by smallest to largest, that solution satisfies all these constraints. And then to prove it's complete, you prove that if something is minimal, there's no way of rearranging it. So I just wanted to mention that part of the reason for the sound completeness is tend to prove it in 2 bits. Now consider value symmetries. So value symmetries are very popular. So once again, now just consider the symmetry of the girls and ignore the rows and the inside each row, the rows reorganized in the data. You can do this just using the Lex-Leader. The Lex-Leader, as normally written, only works on variables. If you Booleanize your problems, the idea is if you have like a variable with domain, like x with domain 1, 2, 3, 4, you pretend it's 4 Booleans. You write like x is, you have a Boolean for x is 1, a Boolean for x is 2, a Boolean for x is 3, a Boolean for x is 4. Now, value and literal symmetries become a variable symmetry on those new Boolean variables. And this is exactly how you break like literal symmetry. You have to introduce all these Booleans, and it feels like a lot of Booleans. There are some constraint solvers, G-code's definitely among them, which do this like efficiently. They have efficient ways of pretending that a variable is a list of Booleans. So it's cheaper than you'd expect it to be. And if you're converting to SAT, you have to turn everything into Booleans anyway. But we can do better than this. Once again, we can do something which is logically equivalent, and I'm going to show it because I think it's very cute. Here, I'm just going to consider the case where you can permute all the values in any way you like. The same idea works for any value symmetry group, but we'll just do the complete one because it's easier to see. So the idea is we start and we'll say the first variable, if all the values are symmetric, we may as well make the first variable 1 because, I mean, they're all symmetric, so let's just pick 1 to fix. For the second variable can either be the same as the first thing or different. But all differents are the same because they're all symmetric. So you can't tell the difference between 1, 2, 1, 3, 1, 4, 1, 5. But you can tell like 1, 1 from 1, 2. So 1, 1 is you've done something, picked one thing twice, and 1, 2 is you've picked different things. And if we had picked 1, 1, then for the third thing, once again, we can either pick another 1 or we can pick a 2. And if we picked 1, 2, then we can pick 1, 2, 1. So we're reusing the first thing or the second thing, or we're introducing a new thing. So the general constraints here is that you just keep track of the maximum value you have ever seen so far in your list. You have another line of variables underneath, and you say the next variable is the maximum of the thing I've seen so far, or it can be 1 bigger, but only 1 bigger because I'm going to let you have 1 more value than you had before. I'm just mentioning that it's very cute. It was by Toby Walsh, I think, originally. So So that's basically all of the easy cases. If your symmetries, if it's just you can permute a bunch of things, great, just order them. If it's nested, great, do each level one at a time. If it's value symmetry, great, do this. Most of the other time, you're in trouble. The classic other type of symmetry that comes up a lot is what's called the product action. So the product action, the classic example of this is rows and columns of a matrix. So we've got a matrix, we can permute the rows, we can permute the columns. And now, of course, when we permute a row, we're changing things in all of the columns. And when we swap two columns, we're changing things in all of the rows. So that nesting business from earlier doesn't apply. The same thing occurs if you have both a variable and a value symmetry. So you can permute the variables and the values. How do we completely break this type of symmetry? Basically, you don't. You don't if the problem's of any significant size. It's too difficult. You can prove it's NP complete to break this symmetry, so you've got no chance. Just going to go back to our row and column symmetry. So this is the classic example of this type of symmetry. So we've got like the matrix, and we have these 12 symmetries. And also, obviously, as the problem gets bigger, we're going to get more and more symmetries. I'm going to pick a few of these out. So consider this constraint I've highlighted. Now, I'm going to do a little bit of highlighting here. Consider this constraint like in action. So this constraint says that A, so the first thing it says is A has to be less than or equal D. If A is equal to D, then B has to be less than or equal E. If B is equal to E, C has to be less than or equal F. If C is equal to F, we go to the next pair, which is D and A. But we'd only get here if we compared the D and A at the start, and they're already equal. So there's no point checking if D is less than A. I mean, A and D are equal, or we wouldn't have got here in the constraint. So this constraint is equal to A, B, C is less than or equal D, E, F. And of course, oh, that's like ordering the rows. That's nice. And similarly, we can pick out two constraints that represent ordering the columns if we simplify them. The point of this is a way of proving that you can take your symmetry breaking constraints for rows and columns, and they are consistent together if you order the rows and the columns in the same way, which is not what I did earlier. And in general, if you have any symmetry group on the rows and the columns, you could break it on the rows, break it on the columns, and as long as you use this underlying consistent ordering, you can chuck all the symmetry constraints together. Now, of course, those three symmetry breaking constraints do not break all of those 12, all the symmetry of those 12 constraints. You can do a bit more. So brief reference again, I'm just going to sneak in a bit of work I did myself. If you look through, you can find that the first row is less than or equal to all permutations of the second row. And in general, you can find that the first row is less than or equal to all permutations of all other rows. So you can pull that bit out. You can write a special propagator. I worked on a special propagator with Alan Frishny and Miguel, and that breaks you a bit more symmetry. But inevitably, like, this is a game that you will not ever completely win. So some people have looked at picking like a row swap and a column swap, and then you break a bit more symmetry. But you will never break all the symmetry without an exponential number of constraints. But you can keep pulling more bits in. But this basic idea of you generate the constraints for each group, and then you just throw them all together in a bag. Sometimes your group might just be like not very nice. In particular, if you got it from graph isomorphism, you might not know that it splits up nicely. Like, how do you pick, if you just have an arbitrary group, how do you pick a good subset of the constraints? And at this point, there is going to be another question. Let me put this up here. Hopefully you can see the code still, 710221. So the idea here is we have a big bag of we have a group that's been given to us by who knows where from. And we need to break the symmetry of this group. How do we pick a good subset of the constraints? A common thing people look at is generating sets. So a set of constraints is a generating set if those members can generate the whole group. So if using them, you can multiply together. The row and column symmetries we used earlier are a generating set. When we do graph isomorphism, like through Naughty, we get a generating set. That's what naughty produces. So what is best if you are picking a set of some given size? So say the generating set naughty gives us is 20. Are we best using the thing that naughty gave us, just any old generating set of size 20, or any old set? Is any old set of size 20 basically as good as any other set of size 20? So like what is it like? Anything's good, generating sets are good, or naughty is good. Remembering, of course, naughty came around long before people. I mean, naughty wasn't designed for symmetry breaking; it was designed for graph asymmetry. So, got some answers. That's good. So great! I'm going to get to teach everyone who answered this question something. Nobody picked the right answer. The right answer is naughty gives superior sets of elements of the group. So I wrote a paper on this. Clearly, no one has read it. I wrote it with my wife, Karen Petrie. If you make random sets of any given size and you check if they are a generating set or not, and then you test their quality for symmetry breaking, whether they are a generating set has zero correlation with their quality of symmetry breaking constraints. This is surprising to many people, but it is absolutely true. We did a whole bunch of experiments. We did everything we could think of. Being a generating set in no way makes you good symmetry breaking constraints. It doesn't make you worse, but it doesn't make it better. However, so I'm going to switch to another graph now. So there's a bunch of points on this graph which I'm going to rediscuss. But so here I have made a whole bunch of random sets of, so I've just taken my symmetry breaking constraints for a problem and randomly picked some of them out. Every red cross is a bag of random symmetry breaking constraints I picked. So you get increasing numbers of constraints along the bottom and decreasing symmetry size. And you can see, broadly speaking, as we pick more constraints, we get more symmetry breaking, although it's not fabulous. This little green cross here is the set of group elements I get from naughty. And you can see that there's not a lot of them. They are better than, so this was allowed you for any significant size group, you can't pick everything. But up here, I have picked like 30 random sets, and none of them are within an order of magnitude. And okay, not quite an order of magnitude. None of them are close to getting the size of search which naughty gets. So there's something about the things that naughty makes which make them really good symmetry breaking constraints. And it's not being generators, because generator is a complete waste of time. I am going to discuss what these other boxes mean if you're curious, so I'm going to come back to them. And the thing that's important is, what's much more important is this concept of truncated constraints. So if we go back to our basic row and column symmetry again, let's just think about things which are less than or equal A. So everything is less than or equal A. If we look down these constraints, like, let's have a look. So like this one tells us that A is less than or equal B, A is less than or equal C, D, E, F. Now, if we look at the, which constraint? Let me find it. This one, number 2. So this constraint says A is less than or equal A. Well, I mean, A is equal A, that doesn't, we could skip that bit. B is less than or equal C. So we know that B is less than or equal C from looking at these constraints. We can deduce that back. And these ones I've listed here are all of the length 1 deductions you can make from these constraints. Now, length 1 deductions are great because for a start, there can only be at most n squared of them. In fact, there's at most n of them. So there is a paper by Pouget where, so he makes the following opposite. He first proves you only need n of these, because if you have A, you'll often get things like A less equal B, B less equal C, and also A less equal C, and you don't need A less than equal C if you know A is less than B and B is less than C. If your problem has a global all different constraint, you know all the variables are different, then actually these reduced constraints are sufficient to break all the symmetry. Because if you imagine going through these Lex constraints, the first time you get to a pair of variables where it's not the same variable in the constraint, then you're finished. You've found all the, like your constraint will either be true or false. And hitting these constraints, it turns out, is a really good way of breaking all the symmetries. So if I just pop back to my graph for a minute, this blue box down here is me adding all of the, just the length 1 constraint. So I take all the Lex constraints, I truncate them all to length 1, skipping assigned variables, and I just put that in. And that turns out to be quite good as a symmetry breaking method. So actually, yeah, so the power, and this makes sense. In particular, it depends on the problem. If you imagine as the domain of your variables gets larger, so the following, like there are problems where the following is extremely not true. So the classic one is a problem called the BIBD, where the following reasoning fails terribly. But in basis, if you imagine you're going through a Lex constraint and the domains are size D, when you get to some pair of variables, you're like, oh, is A less than or equal B? Well, if A is bigger than B, then the constraint is false. If it's less than B, the constraint is true. It's only if they're equal that you need to go on to the next bit in the Lex constraint. And there's only a chance of like 1 over D of that happening. If everything else was equal, in practice, constraints often force variables to take equal values. But that's the kind of hand-wavy idea. Now, I'm going to do a bit of group theory briefly. Naughty and saucy don't just produce generating sets. They produce what mathematicians call strong generating sets. And a strong generating set has the property that, this is like, bear with me, it's a generating set. And if I fix the first k variables for some k, and I take the elements of the generating set that also fix the first k things, they generate what's left of the groups. The idea is it generates the group, and then if I fix the first thing, the generators that fix the first thing also generate all the elements of the group that fix the first thing. The second thing, fix the second thing that generates all the things that move the second thing, etc., etc. This means it generates something close to, not quite, but close to these length 1 truncated constraints. It has to have group elements which fix like the first element if there are things that like, so it will definitely contain a constraint which generates B less than or equals C, because it will have to have a group element that fixes A and does things, and that element will have to swap B and C because that's the only thing left after you've got A. So it will have that element. The best way you can see this, if you imagine you want to break the symmetries of just n variables completely, then we need to say the first thing's less than the second thing's less than the third thing, the third thing's less than the fourth thing, all the way to the second to last thing is less than the last thing. In order to get that symmetry that the last two things are in the right order, the only group element that will get you that Lex constraint is the one that fixes everything apart from the last n minus 2 things, and then swap those last 2 things. That's the only Lex constraint that will get you those last 2 things in the right order. So if you make a random set, there's basically no chance you're going to hit that one constraint that swaps those last 2 things around. But Naughty will have to make that because it has to have ones that fix all the pre. I realize I'm doing this a bit hand-wavily because I don't want to go into the really complicated group theory. There is a paper on this topic called Generating by myself and Karen Petrie. I'll make sure the reference is there, but I want to mention. So the long story short is you can carry on using what Naughty gives you, but don't claim it's because they're generators, claim it's because they're strong generators. Also, just to briefly mention, there are reasons that static symmetry breaking can go badly. So static symmetry breaking works best when your variable and value ordering match the ordering you made the constraints in. So they like a static variable ordering where you follow the ordering the constraints were generated in, and the value ordering that where you go from smallest to largest. If you do that, adding adding Lex-Leader constraints will never make your search bigger. If you don't do that, then you can very well end up with much bigger searches. It's unfortunate. Often you have to choose a trade-off. Do I use the dynamic variable orderings? Because usually they're much better, but they are going to make the search bigger. This is one of the things which SBD, the dynamic symmetry breaking methods, get much better. Because I've been talking for quite a long time and this tutorial has to finish, I am actually going to skip talking about the dynamic symmetry breaking methods. I apologize. This is not an attempt at offending those people who do dynamic symmetry breaking. I'm going to talk about them briefly, but not in the depths that they perhaps deserve. But I will put my slides up and you will be able to see the slides. If you want to ask any questions about it, feel free. So I'm going to briefly talk about the dynamic symmetry breaking techniques. So the first one is called, there's two main ones, SPDS and SPDD, but they follow a very similar theme. They started with this idea called symmetry excluding search trees, then symmetry breaking during search. The idea is that you encode the symmetries as functions that map a partial assignment to the symmetric image of that partial assignment. So now they're not Lex constraints, they're functions that take a partial assignment and map them to different partial assignments. And the idea with SPDS, which is the first one, which is the easiest one. So we've done some amount of search and now we've assigned variable equals value and we did a search and it failed. So we come back and now we're going to do variable is not equal to value. And when we do variable is not equal to value, we can also add the symmetric image of variable is not equal to value. So if we're like, well, the queen isn't here, the queen's also not anywhere else. If that symmetry has not already been broken in the assignments we've done so far. So we apply the function GA to our partial assignment and see if it gives us facts we already know. So we consider the facts we already know as like literals, and we apply the symmetry. And if the symmetry is like still, if this part of the problem is still symmetric, you can tell I know this less well than the static stuff, then we can also add the symmetric image of variable not equal value. So as a like concrete example for queens, we can start by saying like the first queen is not 2. This is the symmetric images of the first queen is not 2. Some of those are like already definitely like not true. Then maybe we say the second queen is 4 or the second queen is not 4. So we can add constraints that say if the second queen is 8, then the fourth queen isn't 7. If the 8th queen is 7, then the 7th queen isn't 5. So SPDS has various advantages. The advantages are it never makes the search bigger. The main disadvantage is you have to keep adding all these constraints as you go through search, and that can be quite expensive. You only need to write these functions with symmetry. So it's very good when you have a small set of symmetries, or you can do like we did with the Lex-Leader and pick a subset. But in general, in experiments, SPDS does less well when you give it a subset than the Lex constraints did. So the key advantage is it respects the heuristic. The disadvantage is you have to do it all the time. Also, Lex constraints, assuming your solver implements them with GAC propagation, can propagate in advance, whereas this reasoning only applies, like it only applies after you've done the search. It doesn't propagate forwards. There is also symmetry breaking by dominance detection, which is a very similar idea. Basically, now rather than like these brute force functions, you do it more in a group theoretic way. So you store the no goods you've already seen and you apply the symmetry. So like you apply a symmetry to, you basically want a function, you basically want a function that says, for the current state, for the current search node, have I ever explored anything that looks like this before symmetrically? Because if I have, don't do it. That's very nicely intuitive. The problem is, how do you detect if the thing that you're looking at is a thing you've seen before? Now you can do this, and there are problems where this is worth doing. So if you have very, very symmetric problems, there are systems that will do this where they will use symmetry breaking computational group theory to detect if what you're looking at is symmetric to anything you've seen before. They can take a ridiculously long time. They can easily take 30, 40 seconds a node just to do the symmetry checking. On the other hand, if your problem's symmetric enough, that's worth doing. The algorithms are complex, and as far as I'm aware, please correct me anyone if I'm wrong, there is no current solver which implements GAP SPD, or the group theoretic version of SPDD. It was in Eclipse which is a constraint solver written in Prolog. Last time I checked, it didn't work. It had broken in Prolog, broken in Eclipse. And as far as I'm aware, it's not implemented anywhere. There are, if you really ever want to test it, there exist old versions of Eclipse and dodgy code in St. Andrews. We can send you a copy. You have to run it from a home directory of a user called Tom, or it doesn't work. That's the level of dodginess. But it has worked. It did work. It did work in very symmetric problems, but it's quite complicated. Sorry. So I now just want to briefly talk about breaking all symmetry. So sometimes, sorry, so I've decided I don't have time to give SBDD the full time it deserves. Sometimes you need to break all symmetry. In my experience, every time this has happened to me, it's been mathematicians. Mathematicians have said, how many of these things are there? I must know how many there are with all the symmetry broken. No questions. There are two ways you can do this. You can just add more symmetry breaking constraints, or you can do post-processing. Adding more constraints is not as crazy as it sounds. So when we were trying to solve, we counted, there's these mathematical objects called semigroups, and we counted how many of them there were. We were typically adding between 10 and 20,000 symmetry breaking constraints to the solver, and we were still getting like 50,000 solutions a second. And you can reasonably add modern constraint solvers. You can add 40, 50,000 symmetry breaking constraints, and they won't get upset by it. SAT solvers are similar. If you have a problem where you, like I have in Minion, given Minion 250,000 symmetry breaking constraints. It only produced like 10 solutions a second. The problems were very easy, by the way. Like it doesn't solve everything 10 solutions a second. But it works, and if you really need to know, you can do it. So don't underestimate how many Lex constraints you can add to a solver. Lex constraints propagators are very, very fast. But sometimes there's just too many. And so what we do then is we find all of the solutions, and then afterwards, we'll try to figure out which ones are minimal. Given a solution, how do we find its minimal image, or if it is already the minimal image? This sounds like a constraint problem. In fact, it is. You could write this as a constraint problem. You could give a solution. You could say, find a way of mapping this to itself such that it gets smaller, and keep applying that and make it smaller and smaller. This is, standard constraint solvers will technically do this, but they are very bad at it. This is basically how Naughty and Saucy work when they do graph isomorphisms. They basically take the graph and they look for ways of mapping the graph to itself. So minimal is what we've been doing so far. You could try to always map the graph to a minimal image of itself. Naughty and Saucy look for what's called a canonical image. And it's just the same as minimal, except basically the equation that describes it is more complicated. So at a very simple level, Naughty might say first put the vertices of degree 1, then 2, then 3, then 4. And then in those graphs, we'll find the like minimal image if we write it as a matrix. So they have a whole bunch of these rules. And then at the end, they say, OK, now we'll just brute force. But as you know from using Naughty and Saucy, if you've used them, they're very quick. I have written a paper on this topic called Minimal and Canonical Images. So this is given a solution to a constraint problem or an assignment in general in a group, it finds its minimal image. Or it finds a canonical image, which is basically if you have two things where you can map one to the other, they'll get to the same canonical image. So you can use this for filtering. What I find interesting, and like I said, I don't have time to talk about this in depth, there's this whole other world like CP in maths, it turns out. So they have things that look exactly like constraint solvers, and they have like a variable, and then they have things which are clearly propagators, but they call them refiners, but they're clearly the same thing. They take the state, they delete values, they have variable orderings, they have value orderings. There's this magic other world of stuff that's basically but not quite constraint programming. And usually these things are used for solving group theory problems. So they're often doing things like trying to find all ways of mapping a graph to itself. So the solutions are permutations which map the graph to itself. One thing that is really weird, but quite cool, is because they are looking for the symmetries of a graph, the solutions to the problem, which are the things that map a graph to itself, are also the symmetries of the problem. So if the solutions form a group, if they're permutations that form a group, that means if you take any solution and you apply another solution to it, you get a third solution. So we don't know what the symmetries are at the start, but as we go through the search, every time we found a solution, we also find some symmetry group of the problem. Actually, it turns out you can just do this with Lex-Leader constraints. You can just effectively, whenever you get a solution, you figure out what group you've got and you just inject more constraints in mid-search and it all works out. Also, these solvers, because they're only for group theory, they typically have like a very limited set of, their variables are more complicated. They'll have a single variable, which is a permutation. But they'll only have, these aren't general solvers. You can't use them for general stuff. They're just for solving group theory problems. So like I say, there's this whole world of this. So if you want to know about this, there's this paper. There's another paper I've written called, with the same authors, called like algorithms for using directed graphs. The most famous paper in this area is a paper called Partition Backtracking by a guy called Jeffrey Leon. I just want to say, the paper is amazing. The work is amazing. Do not try and read the paper. It is the worst written paper I have ever seen. It is super important. It is terrible. I had a 6-month postdoc where my only job was to read that paper, and I didn't manage it in 6 months. But once you understand it, there is this whole world of other constraint-based things. So if you want to break all symmetry, basically the idea is we break as much symmetry as we can in the constraint solver, and then we perform final filtering using gap, using this minimal and canonical images stuff, which is in practice doing another exponential search for every solution. But our hope, and this seems to be true in practice, is they are quick enough that this doesn't cost you a lot. This is too expensive to start doing at every node of search, but it's not too expensive to do on solutions if your number of solutions is already reasonably small. At the moment, how much symmetry we should get the constraint solver to do is tuned by hand. We should probably have some kind of system that figures out how long gap is taking, how long the solver is taking, and winds the symmetry breaking up and down. And the canonical image algorithm is still very expensive. It can take like a minute or two. If you don't have enough objects and you really, really want to know how many there are, you don't care, it takes a minute or two, but it can be very expensive. Anyway, at this point, I'm going to finish, but if anyone has any questions, then I am very happy to take them, or general comments. In particular, if I missed anything out or I insulted anybody, please tell me. There is just too much work in symmetry. So please don't be afraid to jump in and tell me about symmetry work that you feel I should discuss.